Okay, so what if AI research could just run on autopilot? And I'm not talking about some new tool to speed things up a little. No, we're talking about a really fundamental shift, one where AI actually starts to improve itself totally on its own. So let's take a look inside this new reality.
To really get why this is such a breakthrough, we have to start with the problem. And Andrej Karpathy, well, he gave it a pretty blunt name: Meet Computers. Yeah, that's us, the human researchers. For decades, we've been the main bottleneck, right? Manually tweaking code, waiting forever for models to train, basically just slowing down the whole process of discovery.
And the difference in what you can get done, I mean, it's just staggering. On one side, you've got a human researcher, and maybe they can get through a handful of experiments in a single day. But on the other side, you've got an autonomous system that can blow through over 100 experiments overnight. Look, this isn't just a small step up in efficiency, it's a completely different scale of discovery.
So right, how do we break through this human bottleneck? Well, let's meet the solution: an AI agent that takes over the entire research loop.
And here it is, auto research. The best way to think about it is like a tireless junior researcher, is an LLM agent that you just give a goal to and it handles everything else. Coming up with ideas, writing the code to test those ideas, running the experiments, and then figuring out what actually worked. And it does it all on its own. Now, to really get why this is such a massive deal, you gotta look at how we got here. For decades, it was all about Software 1.0, handcrafted deterministic code. Then came Software 2.0, where we started using tons of data to train neural networks. But now, we're stepping into the era of Software 3.0, where the main way you interact with the machine is just natural language. We're moving from coding to just talking. And this whole auto research thing, it is the purest example of Software 3.0 you could imagine. Think about it. A human writes a high-level goal in plain English, the AI writes the code, and the results feed right back into the system. The loop is officially closed. AI is now directly improving AI, all based on a simple human direction.
Okay, so that sounds amazing, but how does this system actually work without just going completely off the rails or, cheating to get a good score? Well, it all comes down to a really clever architecture.
The secret sauce here is something called the tripartite contract. Basically, the whole system is built on 3 core files that have super strict rules about who can change what. And this, right here, is the key to keeping the AI mathematically honest.
First up, you've got the anchor, prepare.py. This file is totally locked down. It defines the dataset and, crucially, the unchangeable evaluation metric. In this case, it's validation bits per byte, which is just a way to measure model performance. The AI literally cannot touch this file, which means it can't cheat by just changing the rules of the game. Next, you have the sandbox, train.py. Now, this is the AI's playground. It's a single Python file with a machine learning model inside, and the agent has total, absolute freedom to rewrite anything and everything in there to try and squeeze out better performance. And finally, we get to the human's new job, the strategic directive, which lives in program.md. And this is just a plain text file. It's where the human sets the high-level goals and constraints in simple English, like telling the agent, hey, prioritize simple code over some crazy complex hack.
So here's the crucial question. How does a stateless LLM, which has no memory of its own, remember what worked and what didn't? The answer is this super clever mechanism called a ratchet loop. It actually uses the Git version control system. Yep, the same tool developers use to track code changes as a kind of episodic memory. Every single time an experiment succeeds, that change is committed. But if it fails, it's instantly thrown away. The system only ever moves forward.
And here's what that loop looks like in action. It is a ruthlessly efficient cycle. The AI reads the goal, it comes up with a hypothesis, it changes the code, and then it runs a super strict 5-minute training test. The metric gets evaluated, and here is the key. If the score gets better, the change is kept. If it doesn't, it's instantly reverted. No time is ever wasted on a dead end.
Okay, all of this sounds great in theory, but what did the agent actually discover? Let's take a look at the results from its very first 48-hour research sprint.
All right, so the process started with a baseline model performance of 1.003 bits per byte. And just remember, for this metric, a lower score is better. So this was the starting line for our autonomous researcher.
After just the first phase, the agent had already made a pretty significant dent. It went after all the low-hanging fruit, adjusting basic stuff like batch size and weight decay, and it quickly dropped the score down to 0.981.
But by the end, after exploring the absolute deepest parts of the model, it achieved this, 0.974. And this wasn't just tweaking a few settings anymore. No, the agent was now rewriting the complex, advanced mathematics of the model's optimizer itself, finding these subtle gains that a human researcher might have totally overlooked.
So, let's put it all together. Over the course of 700 experiments in just 48 hours, the AI followed this surprisingly logical path. It started with the easy stuff, then it moved to bigger architectural changes, and finally it dove deep into advanced optimizer geometry. It even found and fixed bugs that were in the original human-written code. How about that?
This is so much more than just a new tool. It really signals a new reality for engineers and researchers. I mean, what does it even mean to be a human in the loop when the loop pretty much runs itself?
Well, the role is shifting, and it's shifting dramatically. Instead of sitting there typing out lines of code, the engineer becomes more of a swarm manager. Your job isn't to build the thing anymore, it's to direct a whole fleet of AI agents who do the building for you. Your most important skill becomes orchestration.
But, this new reality, it has a psychological cost. People who are working with these tireless agents are reporting a feeling they're calling AI psychosis. It's this constant pressure, this feeling that if you're not giving the AI new ideas to test, you're falling behind. This idea that idle tokens are wasted tokens.
And this brings us to the system's biggest limitation right now, what's being called the creativity ceiling. Because the agent only keeps changes that give it an immediate improvement, it's a phenomenal optimizer. But it can't make a creative leap. It can't take one step back in order to take two giant steps forward. It can perfect the hill it's on, but it can't jump to a whole new mountain.
Which really leaves us with the fundamental question, doesn't it? This agent is an absolute master of optimization. It can perfect any idea we throw at it. But can it truly invent? As these autonomous systems tirelessly climb hills of progress for us, maybe the biggest challenge is figuring out which new mountains are worth climbing in the first place. And for now, at least, that spark of invention, that still rests with us.